Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. For this video, I'll be working through question 9, which comes from exercise 13D of the Extension 1 Cambridge textbook. A student sent this through asking for help in particular on part C, but I'll work through all the three parts, part A, B, and C, just because they all build upon each other, and it's a bit hard to get your head around part C if you haven't already grappled with part A and part B. But what I'll do is, when I upload the video, I'll break it up into chapters so that you can jump straight to part C if that's the only bit that you're concerned with. The question's about differential equations. So we're told that in solving certain problems involving support beams in engineering, the fourth order differential equation y dash 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 equals lambda to the 4 times y is encountered, and it's sometimes written in the notation y bracket 4 equals lambda to the 4y. Part A says to show that y is equal to a e to the lambda x plus b e to the negative lambda x plus c cos lambda x plus d sine lambda x is a solution of the differential equation. Part B says that a beam rests on a support at point O. At a horizontal distance x along the beam, the downward deflection is y, and thus y naught is equal to naught, and we may also assume that y double dash naught is equal to naught. And so for this part, we're told to find the value of capital C. Then part C says if the beam is also resting on a support at x equals 10, then both y10 is equal to naught and y double dash 10 is equal to naught. And from this it can be shown that lambda equals n pi on 10. Now this part C has two subparts. The first says to use these results to show that a is equal to b is equal to 0. And then the second part says to write down the solution of the beam initial value problem, or in other words, when we're dealing with these initial values, what does y simplify to? Alright, so let's just start by writing out this differential equation. So y dash 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 is equal to lambda to the power of 4 times y. That's what we're dealing with. Part A gives us this equation y is equal to a e to the lambda x plus b e to the negative lambda x plus c cos lambda x plus d sine lambda x. And we want to show that this equation is a solution to the differential equation. In other words, it could satisfy such that the fourth derivative of this equation would be in the form lambda to the 4 times the equation. So to show this, we basically just need to differentiate this 4 times and see if we can then write it in this format. So to help with differentiating this, we're basically dealing with an exponential, a cos and a sine, and they're each e to the fx, cos of fx, sine of fx. So it might be worth just noting the derivative with respect to x of e to the fx is equal to f dash x e to the fx. The derivative with respect to x of cos of fx is equal to negative f dash x sine of fx. And then finally, the derivative with respect to x of sine of fx is equal to f dash x cos of fx. So there are the three results that I think are going to help us when we're doing this differentiation process 4 times. So let's just work through it. So let's start by getting y dash. So we're going to differentiate this e to the fx. So we'll have the a, the constant a, stays out the front. Then we'll get our lambda, which is kind of f dash x, the derivative of this bit up here. And then we keep the e to the fx, e to the lambda x. Here we'll have the same thing, but there'll be a negative. So the negative will come out, and then we'll keep our constant b, lambda e to the negative lambda x. For differentiating cos, again, we'll get a negative, so we'll get minus c lambda, and then sine of lambda x. And then differentiating sine, we'll just get plus d lambda cos of lambda x. So that's our first derivative. Now let's repeat. Let's do the second derivative. So we'll get another lambda will come down, so we'll get lambda squared e to the lambda x. Here the negatives will come down, so we'll end up with back at a positive b lambda squared e to the negative lambda x. Derivative of sine, we'll keep this negative here, so minus c lambda squared cos lambda x. And then differentiating cos, we'll get minus d lambda squared sine of lambda x. So that's second derivative. Third derivative will be a lambda cubed e to the lambda x minus b lambda cubed e to the minus lambda x. Differentiating cos, so we'll get back to a plus c lambda cubed sine of lambda x. And then differentiating sine minus d lambda cubed cos of lambda x. Now our final one, y dash 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 dash, will give us a lambda to the 4 e to the lambda x plus b lambda to the 4 e to the minus lambda x. Differentiating sine, so we'll keep our plus c lambda to the 4 cos of lambda x. And then differentiating cos will bring a minus, so we'll end up with plus d lambda to the 4 sine of lambda x. And here we've got a lambda to the 4 all the way through, so I'll just bring that out. Lambda to the 4 times a e to the lambda x plus b e to the negative lambda x plus c cos lambda x plus d sine lambda x. And that is, because this is our definition of y, we can write that as lambda to the 4 times y. So we've got our y dash 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 equals lambda to the 4 times y as required. So we can see that this particular equation does satisfy the differential equation. It can be written in that form. So that's how you tackle part A. Now for part B, we want to find the value of C, this capital C in this equation, noting that we're told that y at an x value of 0 will be equal to 0, and we're also told that y double dash at an x value of 0 will equal 0. So what we can do is we can substitute x is equal to 0 into both our equation and our second derivative and see whether that all combines and simplifies to give us a value of c. So let's start with the equation. So let's kind of put x is equal to 0 here and set y is equal to 0. So we'd have a e to the lambda times naught will just be e to the naught, plus b e to the negative lambda times naught, or just e to the naught again, plus c cos naught, plus d sine naught. So that's all going to be 0. Now e to the naught will simplify to 1, so we'll just get a plus b plus cos of naught is 1, so that's going to just be plus c, and then sine of naught is 0, so the d will drop away, so we'll get a plus b plus c is equal to 0, and maybe I'll call that equation 1. Now if we look at our y double dash and we set lambda equal to 0, we'll get a lambda squared e to the naught plus b lambda squared e to the naught minus c lambda squared cos naught minus d lambda squared sine naught. That's all equal to 0. Now, the e to the naughts, like before, will just become 1. The cos naught will become 1. The sine naught will drop away. And we've got a lambda squared everywhere. So what I can do is I'll say lambda squared a plus b minus c is equal to naught. The lambda squared will drop away. So we'll just end up with, if I move the c over, we'll end up with c is equal to a plus b. And I might call that equation 2. And now what we can do is we can basically combine. So we could say, if I take 2, substitute 2 into 1, what do we get? So we'll get c plus c is equal to 0, or in other words, 2c is equal to 0, or in other words, c is equal to 0. And so that's what we get for part B. The value of this constant in our equation C will be 0. And that now leads us to part C of the question, which is the part that the student who sent this through was really seeking help on. And for part C, it's got 2 parts, but the kind of background detail we're told is that when x is equal to 10, we're told that y is equal to 0, y double dash is equal to 0, and this extra piece of information that lambda is equal to n pi on 10. And the first part of this part C wants us to show that under these conditions, capital A will be equal to capital B and will be equal to 0. That is a possible solution. Basically, that this result can come from these conditions. So kind of quite similarly to what we've just done in the prior parts, we can substitute x is equal to 10 and y is equal to 0, and then same deal with y double dash, and also we can substitute in our lambda and see what happens. So let's start with just y. We'll focus on y. So we'll have a e to the lambda x, or a times e to the n pi on 10 times x, which is 10, plus b e to the negative lambda x, so b e to the negative n pi on 10 times 10, plus c cos lambda x, so plus c times cos n pi on 10 times 10, plus d sine, so d sine n pi on 10 times 10. So that's all going to be 0 since y is 0. All these 10s will cancel, so things simplify. We also know that c is 0 since we've just found that out in part B, so this whole bit can drop away too. So we'll end up with a e to the n pi plus b e to the negative n pi plus d sine of n pi, that's equal to 0. And maybe I'll call that equation, so what have I used? I've used 1 and 2, so I'll call this equation 3. And now let's see what we get when we look at y double dash. So our y double dash, I might just leave lambda as lambda for now so that I can avoid all the complexity of squaring. So we'll have a lambda squared e to the 10 lambda. So we'll have a lambda squared e to the 10 lambda plus b lambda squared e to negative 10 lambda, b lambda squared e to the negative 10 lambda, minus c lambda squared cos 10 lambda, minus c lambda squared cos 10 lambda, minus d lambda squared sine 10 lambda, minus d lambda squared sine 10 lambda. So that's all 0. Remember again, we can drop off the c since we know c is equal to 0. We've also got a lambda squared everywhere, so I'll factor that out. So we'll have lambda squared times a e to the 10 lambda plus b e to the negative 10 lambda minus d sine 10 lambda. That's all equal to 0. Now the lambda squared can just divide out and disappear. And it's at this point now that I might as well put in my lambda equals n pi on 10. So we'll get a e to the 10 times n pi on 10 plus b e to the negative 10 times n pi on 10 minus d sine 10 times n pi on 10. That's all equal to 0. The 10s will cancel each other out just like they did before. So we'll get a e to the n pi plus b e to the negative n pi minus d sine n pi is equal to 0. And I might call this equation 4. And if you notice equation 3 and equation 4, they're very similar, except we've got a plus d sine n pi and a minus d sine n pi. So if we add these up, the d's are going to cancel. So let's take 3 plus 4. So we'll get a e to the n pi plus b e to the negative n pi plus d sine n pi plus a e to the n pi plus b e to the negative n pi minus d sine of n pi. That's going to be 0 plus 0 is 0. The d sine n pi and minus d sine n pi cancel each other out. And we end up with 2 of this. So we'll end up with 2 a e to the n pi plus b e to the minus n pi is equal to 0. You can divide the 2 over. And maybe bring the b over as well. So we'll have a e to the n pi is equal to minus b e to the negative n pi. Divide both sides by e to the n pi. So we'll have a is equal to minus b e to the negative n pi on e to the n pi. And this we can simplify. This e to the n pi in the denominator is just like multiplying by e to the minus n pi. So it'll be minus b e to the minus n pi, which would be minus 2n pi. So that's a. A is equal to negative b e to the minus 2n pi. And maybe I'll call that equation 5. And something we can note, something that will help us, is in part B, we got C is equal to A plus B is something we got, this equation 2. But we also found that C is equal to 0. So that means we know that A plus B is equal to 0. So we can say from part B, we know A plus B is equal to 0. Or in other words, A is equal to negative B. Maybe I'll call that equation 6. And what we can do is I can substitute this equation 6 into equation 5. So maybe I'll turn over. So let's substitute 6 into 5. So what we'll get is instead of A, we can write minus B. So we can say minus B is equal to minus b e to the negative 2n pi. Minus b e to the negative 2n pi. And at this point, if this needs to be true, one way in which this is true is if b is equal to naught. So we can say this is true when b is equal to 0, because you'd have 0 is equal to 0 times something which is 0. So that is b is equal to naught is a value of this constant b that can allow for what needs to be true to hold true. So what we can say is, well, we've just seen that a plus b is equal to naught. So therefore, if a plus b is equal to 0, and we know b is equal to 0, or b being equal to 0 is satisfactory. It's something that it's a value of b that satisfies what we need to be true. So what that would mean is a plus 0 would equal 0, or in other words, a is equal to 0. So therefore, we can conclude that under all these conditions, a will be equal to b, which will be equal to 0, and that's what we were being asked to show. So we could say as required. Alright, now that brings us to part 2 of this part C, which wants us to basically find what y simplifies to under these initial value, the IVP, the initial value problem. So kind of, well, we know a is equal to b, which is actually equal to c. They're all equal to 0, because in part b we found that c was equal to 0 too. So therefore, what happens is we get y is equal to, so if we go right back to our original y, well, a is 0, so this drops off, b is 0, drops off, c is 0, drops off, so we end up with d sine lambda x. So that's our y, is d sine lambda x, but under our initial value problem, we have lambda is n pi on 10. So we can say y is equal to d times sine n pi on 10 times x, and that's it. That's the equation under these initial values. So that's how you work through part C. So kind of really it's a continuation of the techniques that we used in part B, which is why I think it was helpful to kind of work through all these parts. The only difference is you also needed to throw in the lambda equals n pi on 10, but as we see, it kind of we kind of get to a place that allows us to draw the conclusion that we need to. This particular result can hold when b is naught. When b is naught, a will be naught, so a equals b equals naught is satisfactory. It can satisfy what needs to be true. And then because in part B we found that c was naught, it really does simplify under these initial values that we're given in part B and then C as well. The whole equation really simplifies down. Everything drops away and we're just left with this final component. So hopefully you found that explanation helpful. If you did find it helpful, please be sure to give the video a like. And if you're someone who wants to keep your finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.